Well, we'll continue from our last video to look at some symmetry, things that we can do with symmetry for the finite square well potential, or really any even function that's a potential energy function. And I'll do it kind of like we did before in terms of a theorem, and then we'll talk about how to apply that theorem and why it's useful. If if v of x is equal to v of minus x, in other words, the potential energy function is an even function, then we can write the solution, psi of x, to the time-independent Schrodinger equation, which is this thing, h operator on psi of x is equal to psi. So psi is the solution to this. And we can, but from the theorem, we can write that as the linear combination of its even and its odd parts. We can do that for any function, but the thing that's a little bit extra here is where both the even and the odd parts are solutions to the time-independent Schrodinger equation, i.e. That h psi even is equal to e psi even, and h psi odd is equal to e psi odd. Well, there's a variety of ways to go about doing this. Let's look at one of them. First, from our video last time, we know that if the potential is an even function and psi of x is a solution, then psi of minus x is a solution. That was one of the theorems that we proved. And I know that any function, psi of x, can be written, I can extract its even and odd parts. The even part of psi of x is just psi of x plus psi of minus x over 2, and the odd part is psi of x minus psi of minus x over 2. But these are also solutions to the Schrodinger equation, since they are linear combinations of the psi of x and psi of minus x, which are solutions. So since the Schrodinger operator and Schrodinger equation is a linear equation, any linear combination of solutions is also a solutions. So we're able to construct even and odd solutions. Now, to really emphasize some of this, let's take a look at what this implies. I can write psi of x as its even and odd parts. Well, any function can be written in terms of its even and odd parts. That was the theorem we proved in the last video. But here, since v of x is an even function, its potential is an even function, then both psi of x and psi of minus x are solutions to the Schrodinger equation. And now then I can come here and operate on, let's say, one of these, say the even part, with the Hamiltonian operator. And that's just going to be the Hamiltonian operator operating on the even part. Well, the even part is psi of x plus psi of minus x over 2. H is a linear operator, and so it can operate on this sum individually. So it's equivalent to 1/2 times h on psi of x plus 1/2 h operating on psi of minus x. But from up above, h operating on psi of x gives me e psi of x, and h operating on psi of minus x gives me e psi of minus x back again. So these, I use these two equations to get to here. I can factor out the e. What's left is psi of x plus psi of minus x over 2, but that's just nothing more than the even part, psi even. And so by really direct computation, the even part of psi of x also satisfies the Schrodinger equation. You can do exactly the same thing for the odd part. Here I do it. H operated on the odd part. That's h operating on this linear combination of psi of x plus psi of minus psi of minus x over 2. H is a linear operator, so this is equivalent to 1/2 h operating on psi of x minus 1/2 h psi of minus x. Again, from up above, h operating on psi of x, they both satisfy the Schrodinger equation. So this gives me e times psi x back again. H operating on psi of minus x gives e psi of minus x back again. And then again, factor out the e. And we're left then with e times the psi of x minus psi of minus x over 2. And that's just nothing more than the odd. So again, operating on the Hamiltonian operator operating on the odd part, that gives me e times the odd part. So what that says is that we can write at least in the case where the potential is an even function, we can always separate out the even and the odd parts of the wave function that satisfies the Schrodinger equation, and both the even and the odd part satisfy the same Schrodinger equation. Well, we can use that to find these individually. So what we do, and the way this theorem is really used, is that we take a given Hamiltonian. It has to have an even potential energy. Even the potential energy is a function of x, is even function. Okay? And we solve for the even part of it here by solving this equation. And then we solve for an odd function that satisfies it. And then to get the general solution from our even and odd parts, we just do a linear combination of psi even and psi odd to get the full solution. So it has both the even and odd parts of the solution in the full solution. It turns out that looking at the even part or the even part of the wave function by itself usually turns into an easier problem, and looking at the odd part and looking at only for odd functions that satisfy the Schrodinger equation likewise can simplify the problem, and then we recombine them.